Time is tight, so let's kick it off. So, welcome to the Microgravity and Physical Adaptation session number 2. So in the morning we had the ground-based session. Now we'll move up to space, to ISS. And the first speaker is Dr. Claudia Stern. She's the head of the Department of Clinical Aerospace Medicine at the DLR in Germany. And she'll be walking us through the spaceflight-associated neuroocular syndrome, or SANS in short, in astronauts and down-tilt bed rest study participants. So Claudia, the stage is yours.
Could you pull up the first slides, please? Oh, thank you. It has been now 19 years that we saw the first cases with spaceflight-associated neuroocular syndromes. And could you switch? Thanks. And I don't want to go through all the potential pathologies that we see in SANS, because most of you will be very aware of that, and because of the sake of time. In 2020, Patel published this paper, and he was naming SANS as the second risk behind radiation for the health of humans, especially astronauts. How do we define SANS in astronauts? They should have, at least for the definition of the occurrence, one of the following signs, which are refractive error of at least 0.75 diopters, globe flattening, choroidal folds, and optic disc edema, which is defined by an increase of total retinal thickness of about 20 micrometers. And the optic disc edema, this is especially what we are so scared of, because on Earth this always shows an emergency situation. There are potential contributions discussed for SANS, and it's mainly all about the fluid in the upper part of the body, and also the fluid in all the vessels. And also genetics in the meantime, and there had been discussion about an increased carbon dioxide exposure as it is on the International Space Station. We did a head-down tilt bed rest study under CO2 conditions as they are on the ISS, and we saw optic disc edema there too, but we also see it without normal environment, and also the ARED. But we had cases that we saw, and also especially the Russians, of SANS and optical changes before ARED was on the ISS. Ong published a very nice overview about the potential contributions to SANS, and there's always the discussion about the elevated intracranial pressure. So is there an elevated intracranial pressure? We see the changes, typical changes in the MRI, but never has been performed a lumbar puncture in space. And we, all the astronauts that received a lumbar puncture showed only a mild or no increase in intracranial pressure. But we have to keep in mind that the lumbar puncture is only taken usually after 7 days after they return to Earth. So we have no good data on that. And there's also the hypothesis, I will come back to that later on, that there is, that because the pressure in the brain is higher than in the eye, that there is the negative translaminar pressure gradient. Microgravity-induced head-ward fluid shift, because in the subarachnoidal space there is more cerebral spinal fluid now, and that pushes the fluid into the direction of the eye, because normally it's the other direction, and there's a lot of potential pressure also on the optic nerve. That's the idea that also the optic disc edema is created. And this also may inhibit the absorption of the cerebrospinal fluid and also produce problems with the lymphatic decrease there. The secretration may also lead to an accumulation of toxic substances, which also could produce or may be an explanation for choroidal folds and globe flattening. Nedergaard in Denmark was the first one who described the glymphatic system in the brain, and Waston has some publications on the glymphatic system in the eye. And normally there's all the outflow from the eye in the direction through the optic nerve to the brain. And it could be shown only in the rodents, as you see in the lower picture, because there is really the glymphatic outflow from the eye left along the optic nerve. And if this is not possible anymore, because the direction of all the fluids is in the wrong direction now, there might be glymphatic stasis. And that could also reduce the dilution of all the fluids there and increase the optic disc edema. Choroidal expansion, we see that in the astronauts and also in test subjects in bed rest. Because if test subjects and also astronauts are exposed to microgravity, then there is an overload of all the fluid in the neck and the headboard areas, and the choroid drains into that regions. We also have an increase in intraocular pressure in astronauts and also in bed rest participants, and therefore this can, because of all the fluid in the choroid, that could also increase the optic disc edema, and that may be the explanation that some of the astronauts have a real slow recovery of this expansion and also of optic disc. And we also have a few cases of astronauts where there were no reduction of optic disc in finally. Scott Smith and Sarah Swart, they detect very early also that the ones that are affected by the ophthalmological findings have a lower concentration of B vitamins and also the folate, and they went into genetics, and they very, very early described in the first 7 published cases of astronauts that there was an elevation in the 1-carbon metabolism, and also showed that there is polymorphism in the enzymes that are involved in that pathway. They, in the meantime, detected in astronauts and also in bed rest test subjects that there is an elevated number of GLAs in the ones that are affected, but on the other hand, they also showed that there seems to be a protective genotype, the SHMT 1420, because all the ones who have that don't show any ophthalmological findings. We had ESA-NASA working group, and we identified 14 factors that we think should be researched in the future. The main aspect was there on brain, but also on the eyes. And of course, we would like to know what happens to the eyes in missions that are longer than 12 months, and what's the onset rate, and what about the longer missions, and what about when they come back from longer missions. So we recommended this research. Before that, there had been already, for the very first time, the ESA SciSpace-E research roadmap, also with the brain and eye working group. And for that time, the very first time that brain and eye specialists on this topic were brought together. And We also recommended there, earlier as the NASA ESA working group, that we need to see what the effects of countermeasure, develop new countermeasures, and also the short and long-term effects, and especially the effects of age, sex, genetics, and the mission frequency and length, and we also published that. I have the privilege to see the astronauts before and after the missions, especially in our direct return. That means I examine them within the first 3 days of their return, on the one hand side, but also being involved in the bed rest studies as a researcher, but also performing the measurements for the other researchers for NASA and ESA. And especially there, the working horse is, of course, the optical coherence tomography. And the easy and good way there in the bed rest studies is to implement the countermeasures. That's the main question. What kind of countermeasures? Everything that could reduce the fluid shift, of course, like LBNP and pressure cuffs. We also did that in the bed rest studies. And there's a discussion of medication or vitamins for as countermeasures, which means, for instance, the Diamox that has been used in astronauts after they returned and had a mild increased intracranial pressure. And also the vitamin B complex has been given in space already to astronauts, and with potential positive effects there. And we will do also in future for NASA a bed rest study with Ozempic and see whether there's a reduction in optic disc edema there. Coming back to the study itself, if you take a look at, on the right side of the image, you see how the increase of the tissue, the swollen tissue of the optic nerve, as you can see there, you can see that very nicely. And we have the wonderful possibility to really examine it. And as I'm responsible for the health of the participants, we take a look at the ones who have a clinical optic disc edema to ensure their health there. And what we see in the bed rest studies is that mostly the right eye is affected, which is also the case in the astronauts, but there has been a publication now, a case publication of an astronaut who had the left eye much more affected than the right eye, more normally. And it's also females and males. We see that as early as day 10, because everybody says, oh, it's only a long-term issue. No, it's not. It starts early. In some cases, it really starts very early. And there's also this different distribution. You would always think if they have the head down tilt, most of that is in the upper part of the optic nerve. But sometimes it even changes during bed rest with the fluid going to the lower part of the optic nerve. And some have a really steep increase in the beginning, in the center, and some are a little bit more flat, the edema there. So completely different. And but what we see is the longer the bed rest is, the same as with the astronaut, the longer the bed rest, the more optic disc edema we see. And in opposite to the astronauts, it always resolves after bed rest. It can be the case that it resolves right the first day when they get up from the head down tilt. And there's a lot of drainage of fluid. But in others, it takes longer. But within the first 6 months, it always has been resolved. We, of course, want to enable the astronauts in exploration to see whether they have an optic disc edema, and then also to apply countermeasures. That's the important thing. And therefore, we did a tech demo for our retina diagnostics, 30-gram small, light-weighted lens. The astronauts attached it to their iPad and then performed the fundoscopic examinations with the video themselves. And we also developed a program then so that it's really easy without a training to detect the optic nerve. And also we developed now the AI that gives directly a recommendation whether there's an optic disc edema or not. And with that, I thank you very much for your attention.
Any questions? Then please go ahead.
Well, maybe I have to Anna-Maria Lippert from University Hospital Erlangen. I have one regarding the right and left eye. Is that related to handedness? Or can that be related to?
No, we checked that it's not.
Okay.
Good question, we also had that.
And the other question is completely different. You mentioned you have a trial on Ozempic. Can you give a
In the future, this is planned.
And what's the idea?
The idea is that in IIH patients, it has been seen that this reduced the optic disc edema when giving the Ozempic. And therefore, it's a trial whether this also works in bed rest studies.
But then your endpoint is eye-specific and not body composition or any other?
No, it's really, again, an eye study, again. Yeah, that's the question. Because we don't have that really good options in space. And therefore, there's the hope maybe this one may help. Floris, I knew it.
Yes, I'm very intrigued by the riboflavin, vitamin B2. Actually, I don't know if it's used in Germany like that, but in Belgium we use this as the #1 drug against vestibular migraine or migraine. It's really helping a lot, 400 milligrams. So I was wondering, what is the role in this problematic to help astronauts?
So it has been only given once in space so far, and there was also a reduction in carbon dioxide. So we don't know whether it really helped. So the optic disc edema was reduced after 15 days of taking the vitamin B, and this was, let's say, if you look for something to identify what could be the reason, that was very, very early found by Scott Smith, that the astronauts that are affected have a lower vitamin B level. And I can tell you the mechanism of potential help or support there.
Thank you, Claudia. So now we make a switch from the eyes to the bones, and I invite Maura Streghini, Associate Professor from the University of Saint-Étienne in France, to the stage. She'll walk us through osteoporosis, if I'm not mistaken.
Yes, thank you. Okay, so I will be presenting the work done by our unit on the EDOS study, so it's early detection of osteoporosis in space. This is a study done on cosmonauts, 12 cosmonauts, and we want to describe and to understand the prolonged deleterious effects on the skeleton after a medium duration sojourn on the space station. So just a quick reminder that the bone consists of two distinct parts that have different structure and microstructure. So it's the compact bone that we call the cortical bone and the trabecular bone or spongy bone, the two pictures on the right. And the bone is far from a dead tissue, as you all know. It is continuously reorganized and renewed by the activity of bone-producing and bone-resorpting cells. These are the osteoblasts and the osteoclasts, respectively, and their activity is, to a large extent, coordinated by the activity of osteocytes, that are the third type of important bone cells in the bone, that produce molecules that regulate the activity of those cells, as well as hormones that control different parameters in metabolism. And this is because the bone needs to adapt to its mechanical needs. And it's well known that within the physiological range of mechanical loading on the skeleton, there is an equilibrium between bone resorption and bone formation. If the loading is lower, then we have more resorption, and which is on the left-hand side of the graph. And if you have overloading, over mechanical loading, then you have a net formation of the bone. And that means that you have higher bone density, higher bone, more bone. And you can study this in various situations, in the population that is sedentary, for example, in the aging population, various kind of normal pathology, or in astronauts that has show a loss of bone that has been known for many decades, and in analog models on Earth of mechanical unloading. It had been possible decades ago to take biopsies from the bone of bed rest individuals, and it had been shown, even before modern imaging techniques, that the microstructure of the bone changes. And what is interesting is that it is important to really describe and understand and characterize the type of changes at the microarchitectural level, because for an equal extent of bone loss, which is the yellow vertical bar, then the impact on the mechanical properties of the bone is different, whether this bone loss occurs because your trabecular, and this is obviously an example from the spongy bone, from the trabecular bone, are getting thinner, and that's less severe than if you don't get thinner trabecula, but you get fewer of them. You don't need to do invasive biopsies anymore to characterize the bone loss and even the details of the microarchitecture. So on a more large scale, it is possible to detect, like for the general population, the amount of bone mineral density with dual X-ray absorptiometry techniques. But those quantify how much bone you may lose or gain, but don't give you details on the microarchitecture. In the last decades, high-resolution peripheral quantitative computerized tomography, so an X-rays imaging technique, has allowed us to characterize and describe the microarchitecture of the bone. In addition, it's also possible to try to understand what is going on at the level of this potential changes in bone cell activities that could explain why we are losing bone or we are gaining bone. The limitation of this, it's relatively easy technically to do that. The limitation is that we sample the bone, so the circulation, so it's an average systemic effect, and we don't have special information with that, unfortunately. So this is an example, a representation of the loss of bone, and the important message here is that yes, from DEXA studies on astronauts and cosmonauts pulled together, and the important message here is that yes, we do have bone loss, but it's not equivalent across different bone sites, with even some bone sites that are in the orange bar, which is the skull, that gain in bone. So a first study that has already been published several years ago by the group where I now work had characterized bone loss, so this early detection of osteoporosis in space on cosmonauts, and because of the HRP-QCT, so the high-resolution tomography studies, it had been possible to show that there are some sites that lose in terms of quality of the microarchitecture across the period in space, which is the gray bar. You can see that there are some parameters that diminish, so change at least during flight, others that don't. There are parameters that degrade during a flight and then recover with a kinetic that can be more or less fast. And you have, in general, a difference between what we call weight-bearing sites and non-weight-bearing sites or bones. So the bones that are the least, how do you say, the bones that see the least change in terms of the mechanical loading they have don't tend to show a deterioration during flight. So this is the case of the radius, but the tibia, so on the lower limb, it's obvious and it makes perfect sense. What was unexpected back then was that we start to see deterioration of some of the parameters, even of the non-weight bearing bones after return to Earth. And this is a bit of a mystery that we are trying to clarify. So we are, with EDOS-2, we would like to confirm some of those results and especially extend them or extend the period of follow-up to longer times. And this is important because, as you saw before, there is no recovery for some parameters even a year after these individuals, the cosmonauts in this specific case, had come back to Earth. And so the point is, will they ever recover? And so is it, how safe or not would it be from the bone, at least, point of view to send them back to space? So we confirm the data of EDOS-1 in EDOS-2 at the radius. So no degradation during flight, but a progressive accumulation of defects in the post-flight period. Though some parameters that are simulated from finite element analysis tell us that there are already some defects, some structure, some mechanical properties that may already affected during flight, in fact. And we also confirmed the data from the tibia. So this degradation during flight and very bad recovery after. In terms of the cellular activities that could explain those phenotypes, those microarchitectural phenotypes, we are characterizing as many bone markers as we can with the amount of blood that we can get. We get the same similar, we confirm the results that we had in the previous studies. We now can look at more of those markers. What is interesting is that there is a phase about 6 months to a year after return to Earth, where it seems a new equilibrium is established between formation and degradation. But this equilibrium is at a lower level compared to pre-flight. So as if, a new set point is defined, and we don't know yet. And there are some circulating molecules like the undercarboxylated osteocalcin, which is the GLU-OC, which is at the same time marker of bone degradation, bone resorption, by the osteoclast, because it's freed into the blood when there is a resorption. But it is also at the same time, it doubles as a hormone with potential interference on the metabolic pathways, insulin and IGF-1, so insulin-like growth factors 1 signaling. In parallel to our study, a study on astronauts was carried out, primarily on the bone of those astronauts by the group of Steve Boyd. It's interesting to pull together the data and to compare the 3 campaigns, let's say. And we can see some similarities and some differences. So there is a degradation in certain parameters that are observed across the 3 cohorts, others that are not. Then it would be interesting to ask, where do we spot these differences and what could explain these differences that are either at the level of the site, across independently of the nationality, let's say, or the affiliation of the astronauts, we see the same effect, and the differences are among different bone sites, or we see cohort-specific effects. Some of the explanations may lie in the famous fluid shift that is observed in the bed rests and in astronauts, differences at the level of the redistribution of minerals or effects. Also, obviously, the routines and the protocols and the countermeasures that are suggested by these different cohorts of spationauts are different, and that's also where the differences may arise. The amount of time that has been spent in flight before, the length of the flight, all these are important parameters that need to be studied. In terms of the cellular mechanism that could explain the bone loss, preclinical studies that we did with mice that had flown to the space station made us start to look and be interested in the survival of osteocytes, so those cells that are trapped inside the mineralized matrix. And we have already published that there seems to be more cell death about that. But more than just the number of surviving or surviving osteocytes, what is also interesting to characterize is the way these osteocytes are connected among one another in a network. And there are imaging techniques that can be used and quantifications on these techniques that we now start to apply to have a better description of those. Maintaining health and performance of the astronauts and cosmonauts is obviously a limiting factor for the success of future missions, and not only for the bone, but in general, obviously we need to understand more what is going on in order to prevent all the defects and all the problems that may arise. In an ideal world, we would like to adapt countermeasures to the individuals. I think also we should improve how we study. So I hope that a new PhD student that we are about to recruit will be able to perform proper, what I call homeopathic statistics, because the N is so small that we actually need to be able to try to get as much information from the limited N that we have. In order to be able also to look at differences among sexes, where the N is even smaller so far, at least for women, and have a better understanding of recovery periods. So with this, I thank you. I thank you all the people that have worked on the project, both in our unit. This was primarily the work of Peter Fernandez, the third person in the photographs, a former PhD student in the lab, and all our collaborators. Thank you.
So from bone, we move to the partnering crime muscle. So I invite Professor Dieter Blattner from Charité Berlin to talk about muscle biopsy, myotones, and easy motion too. Easy motion. Yeah. There you go.
Thank you very much. Thank you very much, ESA, for inviting me to this workshop. Okay, it was a long day, but I will make the story short as possible. So today I will present 3 studies that have been performed on the ISS with astronauts, and the main idea was to see how skeletal muscle adapts to microgravity, and also how skeletal muscle under the exercise intervention on the ISS, routine exercise, behaves. So I will start with the first slide, which gives you an idea about what will be published hopefully soon in a review. Where are we? We look for muscle pre-post flight, and the experiment also we look for the monitoring of skeletal muscle, so that we will get hopefully acute data, live data, so that the astronaut is able to understand what kind of exercise he needs to perform and what's the outcome of this exercise. So the first one is represented by the muscle biopsy second experiment, the second one by the myotones experiment, muscle tone in space. And number 3, I also would like to tell you something about the Easy Motion 2 experiment, which is in the planning situation at the moment. So let's go on. Muscle biopsy, it's very simple. What we can see here, we take the biopsies before and after flight, after a long duration mission. Long duration means 180 days. And we were lucky to get 5 astronauts at least that gave us the biopsies from the soleus muscle. And we compared this to a short duration astronaut who stayed on the ISS for 6 to 9 days and who did not perform much exercise, so this was a nice control. The 2 articles I will show here. The first one, we looked at the spaceomics and tissue response in astronaut skeletal muscle, and I don't want to go too much into detail, just to show you that we looked into the proteome, and the most important thing was here, we were astonished to see that in the biopsy, in the post-flight biopsy, there were some big changes. And the big changes you can see here. Guess which is the post-flight biopsy, left or right? It is the left one, and the right one was the pre-flight biopsy. And what you can see, there is a destruction, a disturbance in the structure of the muscle. The muscle was, let's say, taken on day 0. Just after landing, there was not so much loading. So we thought, okay, this would probably be some injury after reloading and so on and so on. But then we looked further on. And checked the ECM immunomarkers. We looked for collagen 4, 6, perlecan, MMP, and so on and so on. And you see the results are like this. If you look at the scatter plots, oops, this is, I'm too fast maybe. We see that pre- and post-flight differences in the extracellular matrix. So this means the post-flight biopsies had much less of the collagens expressed, and this would probably, let's say, explain the changes that we see in the muscle tissue. The explanation could be like this. As you probably know, a muscle is not enwrapped only with intramuscular fat, as we have seen today, but is only wrapped of collagen fibers, which is the endomysium. And the endomysium, if you look at the upper left side, the endomysium, you can see here, the muscle cell is inside these little tubes. And if you compare this to the collagen 6A and collagen labels that you can see here in the proteomics, you see the differences between the short and the long duration astronauts. This is probably due to the fact that if you go to the endomysium, the extracellular matrix, you see we have the muscle fiber here, and for example, go on here. These lateral force transmission takes place with the linking of the MMP2 of the perlecan to the sarcolemma, and if the lateral force transmission is lost, this could also mean the disintegration of the muscle fiber. So the next one is the myotones experiment. The myotones experiment is a non-invasive experiment. We had the invasive experiment. Myotones, we used a small portable device that has been used in bed rest before, and now we have used this on the ISS. And the hypothesis was that human spaceflight alters the passive muscle properties. Now, we were not interested in the active muscle properties, but in the passive muscle properties. Why? Because we think that the muscle tone and the muscle stiffness can be used as a digital biomarker for the acute muscle property, and thus helps the astronaut to monitor its current muscle health state. The next video has been used with permission and shows the measurement on the ISS under microgravity. And if you see here, this is the deltoid muscle measured. And the astronaut is in a complete relaxation. So the result was like this. If you look at the digital biomarkers, we measured the Achilles tendon, we measured also the soleus, we measured the tibialis anterior, and we also measured the gastrocnemius. And the most striking result was in the tibialis anterior, because the stiffness was really down compared to the pre and the post-flight results. And also Achilles tendon, we saw that the Achilles tendon stiffness was much lower than before or after the flight. So this means that the tibialis anterior, which is the foot lever muscle, is obviously not well mitigated by the current countermeasure in spaceflight. And if we think that in the future people will be hopping on the moon, that we need something that really is able to activate the muscle stiffness of the tibialis anterior, because otherwise there would be problems in walking. The next experiment is Easy Motion 2. With Easy Motion 2, we want to see if, in addition to exercise, electromyostimulation is able to have a much better outcome of the muscle exercise in space. Easy Motion 2 comprises a suit with the dry electrodes, and the major muscles of the trunk and also of the extremities are activated while the astronaut is performing exercise. And you can see Easy Motion Tech demo 2002 with one astronaut, and he said there that the energy he felt was much higher than without wearing this suit. The step that we will do in the next round, this is the experimental synopsis. We will perform 12 EMS exercises, and we will do myotone measurements before and after the EMS exercise. And with this, we would probably be able to see an additional effect on the skeletal muscle. The problem with myotone and with Easy Motion with myotone, for example, is that you need to have a proper skin measurement points. And the measurement points are usually measured with they are connected by manuals, by adhesive rulers and marker pens, and this is crew time consuming. And we have invented a new system, the new myotone template suite, where we make holes where to measure everything, and we take just this simple device, and the astronaut just wears this suit and then can simply collect the data directly from the customized suit. to summarize, I have shown that the muscle biopsy experiment showed that we have an ECM remodeling that takes place in the astronaut. And also another experiment showed that there is a Ron's homeostasis oxidative stress, which I have not time to go through. The myotones experiment showed that we probably have a non-invasive in-flight real-time feedback, and we can use this probably as a digital biomarker for improved mission crew health management. And with the Easy Motion 2 experiment, we probably will be able to show spontaneous electromyostimulation for improved in-flight exercise. And this would be important because in the future, the spacecraft will get shorter, will get smaller, and we need something that the astronaut gives him more autonomy in future space missions. Thank you very much. It was a long talk, but I hope there will be questions afterwards. Thank you very much. Questions?
Then I give the stage to Dr. Judith Buchheim from Ludwig Maximilian University of Munich.
Yes, thank you very much for the opportunity to speak today. I will report for the project Immunity Assay and for the study group and how this project might help us to understand immunity and the immune changes that occur in space much better. When humans venture into this very unique working environment, which is probably the most unique place to work, they encounter not only colleagues and camaraderie, but also problems and stressors that affect their immunity and their immune system and their performance. It is very hard to find data on incidences or prevalence of these problems. The thought is that they occur very frequently. They have a different appearance, different type of symptoms. This work by Brian Crucian at the JEC in Houston, they try to report how many of these critical symptoms that were worth reporting in astronauts occurred during long-term space missions, and hope you can see it, but it's from 46 crew members, which is for space quite a lot. And what is striking is that we see allergical reactions, we see a lot of skin problems, skin infection, we see congestions, we see prolonged rashes. They can look like this, but only this morning I asked Mike-Britt what her experience is, and she said, oh, well, it occurs so frequently, and it's very unique to the person, and when this person comes the second time to space, they already know, okay, whenever I go to space, I have this and that. So it's person-specific, it's not universal, but it's frequent. So for us, it's, from an immunology point of view, it's a sign of hyperinflammation, inflammation, but also immune dysfunction. So when we looked at cosmonauts in long-term missions, what we can do is, of course, we can count cell numbers, and that has been extensively done, and I think we get the picture. So essentially, if you do pre-post, you see an activation of immune cells, you see a rise in immune cells, but that doesn't tell you much about performance, because it's numbers, and it's not performance. What we can do is we can do cytokine measurements, and that has also been done very frequently in the past, and I think also we get the picture. What you would see in the graph on the right, or the left, or your left, that there is a rise when you go to space for a long-term mission, a rise in cytokines. This one is TGF-beta. And what you can do on ground, pre-post, is you can try to phenotype the cells. So you look for the markers on the surface of the cells, and we did that in that study. And it told us that the regulatory T cells, so that's the T cells that control your inflammation, that resolve inflammation, they were significantly down compared to pre-flight. And similar to that, what we also saw is that some of the memory T cells, the ones you need that for also quickly respond to an immune infection, they shift their type a little bit, and it looks a bit like in the aging situation. So aging population, they become they get a less flexible immune system, and we see similar changes in astronauts. These things seem to resolve, but it still is striking. Now, the problem with this phenotyping is that up to now, you can only perform it post-flight with a considerable quality. And it's always been the question how to address function. Also in this study, what we did is a functional immune assay, where we essentially stimulate the whole blood of astronauts with certain antigens. They can be from fungal origin, they can be from viral origin or bacterial, they can be stimulants, mitogens. There is a broad portfolio. We then incubate the whole blood for 48 hours in that case of the study at 37 degrees. And later on, we take the supernatant and look for cytokines that have been secreted by the cells into the supernatant. And for the same study, Immuno1, we did that for fungal as an exemplary data. We did that for fungal stimulants, and what we saw pre-post only, that there was an overshoot reaction to the fungal antigen. So it's much more after flights what you see when cells release certain cytokines that are responsive to that stimulant. When you compare it to the plasma levels, so this is the graph on the right side of your screen, you see that after flight, the levels are not much higher than pre-flight. So what happens after stimulation? It's not the same what is baseline in your plasma. So the performance is strikingly different than your plasma level. And that's why it's so interesting to run this test also in space. But the problem is you have to have a tube that is closed. You can't pipette any blood in a solution. And at some point you need to collect the supernatant. And you need to freeze this tube afterwards for analysis on ground. So we entered a very year-long validation study where we evaluated different types of materials that could be suitable for this kind of tube. Also the closer, the type of valve that is employed in the tube, and you see it here with the 4 photos on the lower left, no, lower right, sorry. And what you see is you have a tube, you have a clip in the middle, and you have 2 valves on each end. And we looked at, as I mentioned, different types of plastics. We tested several cytokines, we tested several stimulants, we compared everything, but this was the basic principle. We ended up with a tube that was working very well. The next question was, how do we get a defined blood volume sample into the tube itself? So on ground, we would load the tube with the antigen, with the stimulants, and freeze the tube. But how does the astronaut actually get the defined volume of 500 microliter blood into this tube? So for that, we had to run a parabolic flight campaign. And we tried several types of connections. You see the blue valve, you see the ways we tried to find a connection with the blood tube that was sampled. And one big question always is, where is the air? So when you sample blood, you always have air inside your blood sampling tube. And the tricky question was, if you sample in microgravity with the tubes that we are using, is it possible to have the air bubble at the end of the tube, because you want to transfer the blood sample via the blue valve? If there is air, you will not get any blood into your tube. So we had to run a blood draw while the plane goes into microgravity, and we succeeded. And as you can see in the images on the left side, that the air bubble remains at the end. So not like on the ground situation, when you carefully draw your blood and you remain in microgravity, the air is up and the blood remains down. So in the end, we had a tube that we could load directly. You can see myself here trying to load it in microgravity, and it worked very well. So essentially, you can get, what you do is, I didn't tell you this prior to connecting the tube. you do a vacuum, so you aspirate the air, and then that gives you, through the volume of the tube, you get the defined volume of blood into the tube. So that was solved, essentially, and what you get after incubation, on space we do it for 24 hours, you get a tube that is still not separated. So for that, we had to run it place it into the centrifuge, which works well, and then we can clip it again with a clip, and then we have this, what you see on the left, and the plasma we can analyze on ground. We also did on ground several storage tests. So for space, you run your session, and you have to load the sample or the tube sometime on ground, and you upload your tube, and it can happen that it's 6 months prior to your session. So this is while we tested how long are these reagents stable, and it worked very nicely. They still stimulate after 9 months. For the adaptation of the procedure in cubic, because we incubate at 37 degrees, we had an interface designed, and this, as you can see on the left, is harboring 4 tubes. And this is a kick spider insert, so it's for the insertion into cubic. And the nice thing is that we can actually run these incubations at 1G and 0G, which means we can render out the bias of a 0G test, and which will be very interesting when we see the 1G results. And on the right, you can see the first photos after performing the test in space. And I believe it's quite successful. So we had a couple of operators encountering the tube for the first time. They seemed very confident in working with the hardware and very happy about it, because it's something new. It's something where we actually look at performance. We really look into what does your immune system do when it encounters a pathogen, a stimulant. And yeah, we are very happy now that it's finally flying. And of course, such a complex project cannot happen with a lot of helping hands and colleagues that work together. And there are several around the world, and I'm very grateful for them. So thank you for your attention.
So, last but not least, Professor Floriswerts from University of Antwerp will give a glimpse on what happens to the head in space.
Thank you for staying. It's a long day, but I want to show. No, it's on the laptop. Yes. Okay, great. Hope this will work. Good. Who do we want? That was the title which I invented earlier today. Who do we have to send to the moon and beyond? That's a question which I want to respond and offer you solutions. Microgravity, or let's say the absence of gravity, is evident that it has an impact. Actually, the gravity detection, dates back 600 million years ago. So it's kind of like very constant thing on Earth, in species, in creatures. So if you take gravity away, logic that there are some issues. So the otolith system in the inner ear is actually detecting gravity and gives us clues of how to behave, and if we would want to fall, that we can detect that we are going to fall and then act upon. That's our gravity detector. Gravity detection has been investigated in a group of cosmonauts in Star City, where actually it was an experiment as a follow-up of the spin experiment, which was taking place in 1998. And that was actually on board of the Space Shuttle, in the Neuralab mission, where this rotation chair was actually an artificial gravity device. And so the astronauts, 4 astronauts, during the short duration mission were rotated at a speed of 246 degrees per second, providing actually 1G outward. So indeed, this is one of the very first experiments of artificial gravity in space. But this was actually meant to investigate this gravity detector, the otolith system, because it provides eye movements, and eye movements are kind of like mirrors to the inner ear, to the vestibular system. So I This chair is then moved to Star City. And luckily, I hadn't to do this experiment because I think that was even more cruel to do that, particularly on Earth. So, but also again, eye movements, as you can see. Good. So this chair was was moved from space, actually, then to Star City in 2007. And since then, I've been testing cosmonauts before spaceflight and then early after spaceflight. And this is also this chair, the same chair, where it's being rotated. Now this is in Star City. We interrogate what's happening. We are monitoring heart rate. We are monitoring eye movements. A lot of stuff. Very stressful, I have to say, because you only have like one chance. And in the early days after spaceflight, typically the third day, they were still quite tired, so they had sometimes some droopy eyes. So I had to say, eyes open, please, eyes open all the time, okay? So looking at the eyes gave us information about the tilt, the torsion of the eye. Let me explain you the following. If I bend my head to the left, my eyes are counter-rotating to kind of like make the horizon more horizontal. It's a reflex which you can't influence, you can't manage it, it's just a normal reflex. Typically a couple of degrees, 6 degrees. So this is what we did before spaceflight, BDC1, BDC2, approximately 6 degrees, because being spun on this rotation chair provides also a 45-degree tilt, like they were tilted like this. Good. So 6 degrees was before spaceflight. After spaceflight, it decreased to like 2 degrees. The third day, first to third day, then a couple of days later, again, it was a bit more, and then around the 9th day, it was back to base level. Good. But this means actually that early after spaceflight, the detection of the gravity vector is hampered, it's impeded. They don't detect as well gravity as they should, as they did before spaceflight. Now, there's a lot of variability. We all know that. And I happen to not have to use homeopathic biostatistics. I love this term, actually, because we had, in the end, 44 cosmonauts. And if we then thought of why is this variability, then we looked at if they were frequent flyers or if they were first-time flyers. The first-time flyers, they clearly had a much more hampered reflex after spaceflight than the frequent flyer. And it is actually even such that with a series of 44 cosmonauts, we had 13 first-time flyers, 16 who flew 2 times, 8 who have been 3 times in space, 4 times in space, and even 3 who have been 5 times in space. And the more they have been in space, the higher this curve is, which means the more preserved is this gravity detection. Now that's pretty weird because it means that the more you have been in space, the better you can detect 1G, or if you go to moon, 0.16 G. Erik Groen suggested that it may be that 0.16 G could be just around the threshold of detecting. And then there has been some incidents of astronauts on the moon that they indeed lost their equilibrium, but because of perhaps this 0.16 G. So sending people to space, to the moon, you have to send those who have been already several times in space. What is interesting actually is in quite a lot of people of these, we also looked at the brain, because actually it was kind of like a parallel experiment. First they were rotated on this chair, and then they were scanned in the scanner in Moscow. And we found actually that there was a correlation between how the hub for the vestibular system, operculum parietale 2, which is really the vestibular cortex, how that is communicating with the angular gyrus. And the more it is communicating, the better this reflex is preserved. And you see on this line, it's really showing on the right side the early flyers, the first-time flyers, on the left side the repeated flyers, and horizontal is on this axis indeed the amount of connectivity, which is changed before and after spaceflight. So we now know why this reflex is indeed impeded. So definitely this is the paper from Kato Schoenmakers 2 years ago, where she really very nicely used these statistics and analyzed all this data. So we have to send people to space who have been there already. But that's not all. If we send people to space, we have to preserve their health. Now, the Brain DTI project is actually looking at the brain before and after spaceflight. And there we found a couple of, well, remarkable things. One of them is the upward brain shift. Now, this is a GIF prepared by Stephen Gillings, one of my postdoc in my lab, and you can clearly see 3 time points: pre-flight, immediately post-flight, and 6 months later. That's the follow-up. And you can, with your naked eye, you can see that the brain is really shifted upward in the skull, which means that the sagittal sinus is being squeezed. There is a hampered regulation of fluid. Fluid shift is particularly, I mean, you can really see it, and also the ventricles are increasing, are inflating. This is a paper by Angelique some years ago, where indeed we could identify that the ventricles, they inflate after spaceflight, like 13% for the lateral ventricle, the third ventricle, but even 6 months later, and that's a bit in parallel with the bone story, 6 months later, but brain is not bone, that even 6 months later there is still a preserved inflation of these ventricles, which is not really what we would expect. Okay, so that's only one part of the story. I was happy that I had a perfect intro of sounds by Professor Stern. So, okay, I'm not going into this, but this is indeed a showstopper. It's a game stopper, well, a showstopper for going to space. Now, okay, Giuseppe Barisano contacted me some time ago, and he said he had a pipeline to investigate the perivascular space. Now, the perivascular space is actually the space around the blood vessels in the brain. So, I mean, it's the same like typically if you have tubes in your home, you have a tube around the electricity tube. So that's actually also a perivascular space. So, and that perivascular space is used as a sewer of waste products coming from the brain, like amyloid and tau. So, okay, the question is, well, we had a HRP conference in Galveston, and the fantastic thing about this type of meetings is that you talk to each other and you say, okay, can we do something with our data? I mean, that's fantastic, and I really thank ESA for organizing this and also to let me speak. So at this conference, we started talking with Donna Roberts, who had a group of 24 NASA crew members, 7 shuttle flights. At that time, I had 4 ESA crew members tested and 13 Roscosmos crew members together with Elena Tomlovskaya. And this is the perivascular space after spaceflight. For the controls, just people who did not go to space, after 6 months increases like up to 5%. The Russian cosmonauts, 12%. The NASA members who had not SANS, they increased up to 22%, and the NASA crew members who had SANS, even more than 30%. Shuttle flight doesn't affect. Now, this is really bizarre, because actually, I can show you images of how this white matter perivascular space is increased. On the right side, you see before, and on the left side, you see after. Yes. So that's for the white matter. For the basal ganglia, this is what you can see. It's a bit more subtle, but also on the right, on the after spaceflight, it clearly increased. The subarachnoid space at the vertex, you see on the right, well, for me, the right side, the after spaceflight, there is fluid which is being pushed away. That's why you see it a bit more like with holes in there. And then this one is the ventricles. You can clearly see after spaceflight increased ventricles. So that is not really like an interesting observation. Well, it's an interesting observation, but if people ask me now, would you like to go to space? I say, oh yeah, sure, 2 weeks, and that's it. Because not 6 months, because that's what happens with your brain after 6 months. Here you see also post and pre for the Russian crew members and for the NASA crew members. Now it is clearly visible that there is something going on there, particularly in the NASA crew. Question is, what's the difference? On the previous talk was also about that. What's the difference? They're all in the same habitat, all being launched with the same, at that time with the same Soyuz, breathing the same air to a certain extent, eating the same food, even that we know. Well, it's not on paper, but they swap food because otherwise it's too boring, so they really swap food. So, yeah, they all drink the same purified urine from yesterday. So, what is the difference? And I was happy that the same picture was also showing earlier on. LBMP is what the Russians do, on one hand, and ARED, they both do ARED. But I'll demonstrate what Samantha Cristoforetti showed me the day after she returned, because I was talking to her about this phenomenon which we observed. And she said, yes, but the Russians, they also do ARED. And then she said, oh yes, but they do it like this. So no load, hardly any load. Whereas the American crew members, they really they induce, perhaps, Valsalva maneuver. And repeated Valsalva may increase in the fluid shift. So we hypothesize, and in the beginning, the people didn't like us to say that, because there's a large group of people who say, yeah, ARED is fantastic. It's a big lobby to say, you have to do ARED, and I believe that. For bone and muscle, yes. But if it's not good for the brain, that's a difficult situation. So the PNAS paper was about showing this data. And now I see popping up this hypothesis, indeed, ARED. Is that showing it, yes or not? And Professor Stern also mentioned it. So it's still a working hypothesis. So to close my talk, take-home messages, very easy. Send people who have experience, and perhaps even repeated experience of going into space. Being there, done that, I think it's crucial to survive or to perform at its best, particularly going to the moon. And then after that, think about impact and side effects of specific countermeasures on the brain. That's what I wanted to tell you. I want to just show some, I want to thank obviously all the participants of my experiments. You don't do science by yourself. You have to have a team. It's crucial to have a team, and also the participation, and to think together, and to brainstorm together, and to like each other, because then you can do fantastic work. If you like each other, you accept that the other has a better idea than yourself. That's crucial for good science. So my team is also crucial in the whole story. They just participated parabolic flight recently, and so thank you for your attention. Within time, I respect a bit the time.
So, thank you all. So first of all, thank you to all the speakers for contributing to this session. It was interesting talks. Food for thought, for sure. I think we should close this session now because we're a bit over time. But that's the lessons learned from our side, that we need at least need a session of 1.5 hours, so we can at least enable some discussions and have the opportunity to have some more questions. But I invite everyone, if you have any more questions to one of the speakers, then just approach them. They're here, I hope, until tomorrow. So yeah, have a nice evening, enjoy the night, and then we'll see you all together again tomorrow. Thank you.